Imagine an intelligence that isn't just a master at one thing, like playing chess or effortlessly finding information for you.
Right.
Instead, picture a system that can learn anything you throw at it, adapt to entirely novel situations, evolve its understanding, and really comprehend the world in a profound human-like way.
Yeah, it's not just sci-fi anymore.
Exactly. This isn't merely the stuff of far-off science fiction anymore. It's the profound, fascinating frontier of artificial general intelligence, or AGI.
It's a concept that truly stretches the boundaries of what we thought was possible, and maybe surprisingly, what leading researchers and engineers are actively trying to build right now.
And today, we are taking a deep dive into AGI. We're going to unpack what it truly is, tracing this incredibly ambitious idea from its earliest roots right up to today's cutting-edge developments.
Yeah, and we'll explore the diverse and sometimes really surprising ways researchers are approaching building it.
And then confront the massive technical challenges and, frankly, the profound opportunities it presents for all of us.
To give you this comprehensive understanding, we've pulled from a foundational report titled AGI, Concept, History, Progress, but also alongside numerous academic papers, industry insights, and, the latest discussions from the front lines of AI research.
Our mission today is to cut through the often confusing rhetoric, try to give you the essential understanding, and maybe unearth some surprising facts that will leave you genuinely well-informed about this pivotal topic.
Because this isn't just about faster computers or, smarter apps on your phone.
No, not at all. This is about systems that could fundamentally transform human civilization, impacting everything from how we work, how we learn, how we create.
Even how we relate to intelligence itself. It's huge.
So how do we ensure that such a profound capability serves humanity's best interests in the long term? Moving beyond just economically valuable work to perhaps foster deeper human flourishing.
That's the million-dollar question, isn't it?
It really is.
Yeah.
And it's a question we'll keep circling back to today as we unpack what AGI truly means.
Okay, sounds good.
Let's start with the absolute basics then, because the term AGI gets thrown around a lot, often leading to confusion. What even is AGI?
Yeah.
We often hear about AI that can do incredible things, but almost always it's in a very specific, limited area.
That's exactly right. And that distinction is crucial. The core concept of AGI is thinking about a theoretical software system, right? One with intelligence broadly comparable to a human's.
Comparable to a human.
Yeah, capable of self-teaching and adapting across a vast array of tasks and domains. That breadth is key.
Okay, so contrast that for us with what we usually encounter, the narrow AI.
Right. You need to contrast it directly with what we call artificial narrow intelligence, or ANI. Think of ANI as specialized tools. Brilliant, maybe, but like a savant excelling in just one specific niche.
So like IBM's Deep Blue, the chess-playing AI that famously beat Gary Kasparov.
Exactly.
Or, those sophisticated medical diagnostic tools that can analyze scans with maybe even superhuman accuracy in that one task.
Exactly. These are incredibly impressive, even superhuman, like you said, in their specific tasks, but they are meticulously optimized for specific, well-defined functions.
Deep Blue couldn't then turn around and write a compelling novel or debate philosophy,
Not a chance.
much less operate a robot arm. It's just confined to its domain.
Exactly. And that's where AGI fundamentally differs. It's all about generalization. That's the core idea.
Generalization.
Meaning an AGI system would possess this remarkable ability to apply knowledge it learned in one situation to entirely unfamiliar situations. It could adapt to novel problems without needing explicit reprogramming for every new challenge.
So it's not just recognizing patterns it's seen before.
No, it's recognizing new patterns in entirely new contexts. It's deeper.
So it's not just rote memorization or pattern matching within a limited scope. It's about true understanding and transferability of knowledge.
That's the goal, yes.
What are some of those other key AGI attributes that truly set it apart?
Well, beyond generalization, we're talking about advanced self-learning and adaptation. An AGI system would continuously refine its outputs and acquire new skills through experience and real-time interactions.
Like a human learning over their lifetime.
Kinda, yeah. Then there's autonomy, the idea that an AGI could make independent decisions without constant human intervention. It wouldn't just follow commands. It would initiate actions based on its own understanding of its goals.
That autonomy part sounds, well, potentially revolutionary or maybe even a bit scary depending on how you look at it.
It definitely raises questions, and some researchers even suggest it could potentially develop a form of self-awareness, though that's highly speculative and philosophical.
Right, the self-aware bit is really out there for now. But even without that, it would need some serious cognitive horsepower to match us, wouldn't it?
Absolutely. It would have to encompass sophisticated reasoning and problem-solving abilities, allowing the system to logically deduce solutions to complex, multi-domain problems, even in contexts it wasn't explicitly trained for.
So connecting the dots, finding underlying principles.
Exactly, devising novel strategies. And finally, AGI aims for holistic integration of multiple cognitive functions: perception, language comprehension, memory, decision-making, all unified into a coherent, interacting system.
So it's not just a collection of smart modules bolted together.
No, the aspiration is for a truly comprehensive, adaptable, and integrated intelligence, a unified whole.
Okay, that makes the distinction from ANI very clear.
Mm.
But there's another term that often gets mixed up with AGI, artificial superintelligence, or ASI. How do those two relate? Are they interchangeable? People use them together sometimes.
They get conflated a lot, but no, not entirely interchangeable. What's fascinating here is that while AGI strives to achieve intelligence on par with human capabilities, to be roughly as smart as us across the board.
Okay, human-level general intelligence.
Right. ASI is a hypothetical stage beyond that, where an AI would vastly outperform humans across virtually every domain, not just specific ones.
Ah, okay. So AGI is the getting to human-level part, ASI is the going way beyond part.
Pretty much. Think of it this way. AlphaFold's impressive prowess in protein folding, or AlphaGo's mastery of the game of Go. These are examples of superintelligence, but only in specific tasks.
Still narrow AI, fundamentally.
Exactly. Still narrow AI, lacking the broad generality of AGI. ASI is, in essence, conceived as a type of AGI that transcends human intelligence by a wide margin. It's AGI, but vastly more capable, faster, more efficient in every cognitive respect.
So AGI is human-level or comparable across many domains, and ASI is human plus 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 across everything.
Yeah.
That helps clarify things.
Yeah, it's a useful distinction.
And it seems like the very definition of general intelligence itself is evolving, especially within the leading AI research organizations. It's not just a static theoretical construct anymore, is it?
No, definitely not. And this raises an important question. How do we even begin to measure progress towards something so profound and potentially transformative? It's tricky.
Right, how do you benchmark AGI?
Well, OpenAI, for instance, has offered a particularly pragmatic definition, which has caused some debate. They define AGI as highly autonomous systems that outperform humans at most economically valuable work.
Economically valuable work. Huh. That's a very pragmatic, maybe even industry-driven shift, isn't it?
It is. It frames the goal around utility and market impact.
But what does that emphasis on economic value mean for how we track progress? And perhaps what values are implicitly embedded into the very definition of this profound intelligence?
That's precisely the fascinating philosophical and societal implication.
Are we saying if it can replace a lawyer, a doctor, and a programmer, then it's AGI, even if it can't, say, genuinely appreciate a sunset or show true compassion? Is utility the only measure?
That's the crux of it. This redefinition doesn't necessarily mandate replicating every nuance of human consciousness or emotional intelligence. Instead, it prioritizes broad competence in domains that yield tangible economic impact.
Which could accelerate the perception of AGI's arrival, I suppose, as systems get better at automating high-value tasks.
Exactly. It highlights a tension between building machines that are simply useful and those that might truly understand or experience the world in a human-like way. It challenges us to ask, are we building intelligence in our own image, or are we building a new kind of intelligence defined primarily by its utility to us?
That's a deep question. And Google DeepMind has gone even further, creating a more granular classification framework for this, haven't they? Trying to put some real structure around these definitions, moving beyond just vague notions.
Yes, in 2023, Google DeepMind researchers proposed a really detailed framework. It aims to track AGI progress by looking at both performance and autonomy.
Okay, performance and autonomy. How do they break that down?
So for performance, they define levels like emerging, which they say is comparable to an unskilled human. That's where many current large language models like ChatGPT or Llama 2 might fall in their general capabilities.
Okay, emerging. Then what?
Then it progresses up to competent, meaning it outperforms 50% of skilled adults in diverse non-physical tasks. Then expert, virtuoso, and finally superhuman, which means outperforming 100% of humans.
Wow, quite a ladder. And the autonomy levels. That speaks to how much help it still needs, right?
Exactly. Those range from tool, where it needs constant human prompting, like most current systems,
Right.
to consultant offering advice, collaborator working alongside humans, expert managing complex tasks, and ultimately agent, meaning fully autonomous, making decisions and executing actions without constant human oversight.
So this framework gives a more structured way to assess where we are. Like with GPT-4, its performance sparked a lot of this emerging AGI talk.
It did. GPT-4's impressive performance across diverse domains, mathematics, coding, law, really fueled that debate. It showed capabilities comparable, in some ways, to an unskilled human, but crucially, across many different domains simultaneously. That breadth was new.
Okay, that helps ground it in something more concrete, a measurable path, even if the end goal is still debated. Now, there's also this philosophical nuance we should touch on, John Searle's strong AI. It often gets used interchangeably with AGI in popular discussion, but there's a key distinction, isn't there?
There is, yeah, and it's a subtle but really critical one. While people often use them interchangeably, strong AI, as the philosopher John Searle discussed it, sometimes specifically implies more. It suggests a computer program would possess actual sentience or consciousness, a mind in the human sense, with subjective experiences, feelings, internal states.
Okay, so strong AI implies consciousness. How does AGI differ then?
AGI, conversely, primarily focuses on achieving human-level cognitive abilities, things like reasoning, problem-solving, learning, adapting. It doesn't necessarily mandate subjective experience or consciousness.
Ah, so we could potentially work towards AGI, build systems with human-like cognitive skills without having to solve the deepest mysteries of consciousness itself. That's a significant distinction for researchers, isn't it?
It is hugely significant. This subtle but critical distinction means that AGI research can advance significantly without necessarily resolving the profound philosophical, hard problem of consciousness, which, frankly, we're nowhere near solving.
But the public perception might still link them.
Absolutely. The frequent conflation of these terms in broader discourse indicates that for many people, the notion of true general intelligence remains intrinsically linked to some form of subjective awareness. It's hard not to imagine it that way.
Yeah, I can see that.
And this continues to shape public perception, ethical considerations, and even the fears people might have about AGI, even if consciousness isn't the direct technical goal within the labs right now. The public's imagination often runs ahead of the scientific definitions.
Which is why clarifying these terms is so important. Okay.
Absolutely.
So if we pull back a bit then, what's the overarching vision for AGI? What's the ultimate goal beyond just these technical definitions and benchmarks?
Well, the overarching vision, the grand ambition of AGI research, is really to engineer machines that can not only replicate, but potentially even surpass the entire spectrum of human cognitive abilities.
Replicate and surpass, that's a profound goal. What does that spectrum truly include? What human abilities are they aiming for?
It's incredibly broad. It encompasses intricate capabilities like complex, abstract reasoning across multiple domains, not just one, genuine creativity going beyond merely generating novel combinations of existing data to true, insightful innovation.
Real creativity, not just remixing.
Exactly. Nuanced emotional intelligence, understanding and responding to human emotions appropriately, which is incredibly hard. And the capacity for continuous lifelong learning from diverse experiences without just forgetting previous knowledge, which is a big problem now.
A catastrophic forgetting issue.
Right. The aspiration extends beyond mere task execution to achieving a profound understanding of context and meaning, coupled with the adaptability to navigate and interact effectively within the complexities of the real world.
It's a quest for artificial entities, then, not just sophisticated tools.
You could say that. It represents a quest for artificial entities that can truly comprehend, innovate, and evolve in a manner analogous to human intellect, not just mimic specific behaviors perfectly.
That really does change the landscape of our potential future, doesn't it?
Yeah.
Wow. Okay, that gives us a solid foundation for what AGI is. Now let's take that whirlwind tour through AGI history. Because this ambition, this dream of creating machines with human-like intelligence, It isn't new at all, right?
Not even close. It actually dates back to the very origins of computational theory, stretching way back to the 1950s and the dawn of what we now call symbolic AI.
The 1950s, so right from the beginning of computers almost.
Pretty much. The audacious dream of artificial general intelligence can be traced back to the burgeoning field of computational theories back then. Visionaries like John von Neumann.
The computer architecture pioneer.
That's him. He was already exploring the possibilities of replicating the intricate functions of the human brain within mechanical systems. He even wrote a seminal work called The Computer in the Brain back in 1958.
So he was laying the intellectual groundwork, thinking about machines not just as calculators, but as information processors capable of complex, brain-like operations.
Exactly. And then, of course, there's Alan Turing. His groundbreaking 1950 paper, Computing Machinery and Intelligence, introduced the profound idea that machines might one day exhibit intelligent behavior indistinguishable from humans.
And the Turing test came from that, right?
It did. He didn't just theorize, he proposed the famous Turing test as a foundational concept for evaluating such intelligence based purely on observable behavior. It effectively shifted the focus from how intelligence is achieved biologically to what it can do functionally. Can it fool you into thinking it's human?
A very pragmatic approach.
Yeah.
So these initial ideas laid the groundwork for the first real attempt at building AI, the era of symbolic AI, sometimes called GUFAI.
Yeah, good old-fashioned AI, or GOF AI. In the 1950s and 60s, prominent researchers Alan Newell and Herbert A. Simon advanced the physical symbol system hypothesis. This was huge.
Okay, what was that hypothesis?
It basically asserted that a physical system capable of manipulating symbols like words, numbers, logical operators possesses the necessary and sufficient means for general intelligent action. It formed the bedrock of symbolic AI.
So the idea was, if you can represent all human knowledge as explicit symbols,
Right, like cat or is-a or greater than.
and then manipulate those symbols using logical if-then rules, you could achieve general intelligence. It was all about formalizing thought into logical rules.
Exactly, like a very, very complex rule book for thinking.
And a big early win for symbolic AI was the logic theorist, developed by Newell and Simon in 1956, wasn't it? That was considered the first true AI program.
It really was, yeah. Its ability to prove theorems in symbolic logic, taken from Whitehead and Russell's Principia Mathematica, was a significant intellectual achievement. It must have seemed incredibly promising at the time, suggesting that logic could really crack the code of intelligence.
It definitely fueled enormous optimism, I bet.
Oh, absolutely. But despite these early successes and the initial excitement, symbolic AI eventually hit some major roadblocks. It struggled with the immense complexity, ambiguity, and just the sheer messiness of the real world.
Right. The world isn't always logical and clean.
Far from it. It turned out to be incredibly difficult, maybe impossible, to hand-code all the rules and exceptions of human knowledge, especially common sense reasoning, which we use constantly without even thinking about it.
Like knowing you can't walk through walls or that water is wet. How do you write a rule for all common sense?
Precisely. This limitation ultimately led to a period of reduced funding and interest in the field, starting in the mid-70s and deepening in the 80s. It's often referred to as the first AI winter.
The AI winter.
Yeah.
Because the funding dried up.
Yeah, the hype cycle crashed. It highlighted that while pure logic was powerful, it simply wasn't enough on its own to capture the fluid, intuitive, often uncertain reality of human intelligence. The rules just got too complex and brittle.
So the field hit a snag, a true winter. But then, it wasn't too long before we saw a dramatic resurgence, shifting away from pure symbols to something more brain-like. Connectionism and machine learning. This was a completely different paradigm, wasn't it?
Indeed. The landscape of AI research began to shift dramatically again in the 1980s, experiencing a significant resurgence. A second spring, if you will.
What drove that resurgence?
Well, it was partly fueled by the practical utility and commercialization of early expert systems, which used symbolic rules but were very focused, mimicking human expertise in specific domains like medical diagnosis or configuring computers. They showed AI could be useful.
So practical applications helped.
Yes, and, more critically, concurrent advancements in computer hardware finally provided the necessary computational muscle to run more complex models that had been theorized earlier but were just too demanding computationally.
And this brought neural networks and connectionism roaring back into the spotlight.
Exactly. This was a fundamentally different approach. Instead of explicit rules, it drew inspiration from the structure and function of the human brain itself.
How so? What's the core idea?
This approach posits that knowledge isn't explicitly programmed as symbols and rules. Instead, it emerges from intricate patterns of connections and adjustable weights within networks of artificial neurons. Learning becomes a dynamic process of modifying these weights based on exposure to vast amounts of data.
So it learns from examples, kind of like how biological brains adapt through experience.
That's the inspiration, yes. And a pivotal breakthrough that really rekindled interest was the popularization and refinement of the backpropagation algorithm in the mid-80s by researchers like David Rumelhart, Geoffrey Hinton, and Ronald Williams.
Backpropagation. That sounds important. What did it do?
It provided an efficient mathematical method to train multi-layered neural networks from data. It allowed the network to figure out how to adjust all those internal connection weights layer by layer to reduce errors, enabling them to learn complex input-output mappings. It unlocked the potential of deeper networks.
That sounds like a true game changer for neural networks. What other breakthroughs defined this era, pushing connectionism forward?
Well, further theoretical advancements built on this momentum. John Hopfield's introduction of Hopfield networks in 1982, for example, showed how neural networks could function as content-addressable memory and tackle optimization problems. They could find good solutions to complex problems, not just classify patterns.
Interesting. And Hinton was involved again later with Boltzmann machines.
Yes, Geoffrey Hinton and Terry Sejnowski's development of Boltzmann machines between 1983 and 1985 was another key step. They advanced neural network theory by introducing concepts like distributed representations and probabilistic reasoning. This opened the door to systems that could handle uncertainty and ambiguity, a major weakness of early symbolic AI.
Dealing with the messy real world again.
Exactly. And we shouldn't forget the earlier foundations of unsupervised learning. Ideas like Donald Hebb's famous cells that fire together, wire together principle from way back in 1949.
The Hebbian learning rule.
Right. And Tuvo Kohonen's self-organizing maps from 1982. These laid crucial foundations for systems capable of discovering meaningful patterns and structures in data without explicit supervision or labeled examples. This whole era, the 80s and 90s, really set the stage for the deep learning revolution we're seeing today.
And what we see today is truly incredible, especially in the last decade or so. We've reached the era of contemporary progress in the current landscape, from the 2010s to the present. It feels like we're constantly breaking new barriers, almost weekly sometimes.
We really are. The 2000s and especially the 2010s witnessed significant, almost unbelievable strides in engineering specialized AI capabilities. Fueled by massive data sets, powerful GPUs, and refinements in deep learning algorithms, AI achieved superhuman proficiency in many highly constrained tasks.
This is where we get things like Google DeepMind's AlphaGo, right?
Yeah.
Famously defeating the world champion of Go, Lee Sedol, in 2016. That felt like a major moment.
A huge moment. And before that, IBM's Deep Blue triumphing over Garry Kasparov in chess back in '97, and IBM's Watson winning Jeopardy in 2011, showcasing really advanced natural language processing for the time.
These were mind-boggling feats, capturing the public imagination and showing the power of AI.
They absolutely were, and they proved the immense power of focused AI development. But, and this is crucial to reiterate, while incredibly impressive, these systems remained fundamentally confined by their narrow focus. They lacked the multi-domain adaptability characteristic of true HEI.
Right. They were super specialists, not generalists. AlphaGo could play Go brilliantly, but couldn't then, write a coherent email or diagnose a medical condition.
Exactly. But then came the rise of large language models, or LLMs, really exploding in the 2020s. This feels like a completely new phase, one that's really blurring the lines between narrow and general AI in the public consciousness.
We're talking GPT-3, ChatGPT, Llama 2, Claude, these so-called foundation models. They've shown remarkable content generation abilities, but more importantly, some initial signs of cross-contextual transfer learning, a surprising breadth of capability.
What's truly fascinating here, and quite controversial, is that while most researchers wouldn't call them full AGI yet, some, including researchers at Google DeepMind, have begun categorizing them as emerging AGI.
Emerging AGI, meaning?
Meaning they might represent a nascent form of general intelligence, maybe comparable in some respects to an unskilled human, but showing sparks of generality across tasks.
And OpenAI's GPT-4 really pushed this conversation forward, didn't it? Its performance was stunning.
It really was. GPT-4 demonstrated capabilities close to human-level performance across remarkably diverse domains, things like mathematics, coding, even passing standardized tests like the Uniform Bar Exam with a score in the top 10%.
Passing the bar exam. That's something previously thought impossible for an AI. It truly fueled the debate about whether this was an early glimpse of AGI.
It absolutely did. And OpenAI isn't just making models bigger. They've introduced something called O1 preview models recently, which seem to represent a new paradigm.
How so? What's different?
They're described as spending more time thinking before they respond. The idea is to improve the quality of the output through increased computational effort during the generation process itself, not just by having a larger model initially.
Interesting. So almost like an AI that pauses to reflect or reason more deeply before answering. That's a subtle but potentially very significant shift.
It shows an evolving understanding, perhaps moving beyond just statistical pattern matching towards something more akin to deliberate reasoning, even if it's still simulated.
And if connect this to the bigger picture, AGI isn't just a theoretical pursuit in academia anymore, is it? It's a primary objective for leading AI companies globally.
Oh, completely. A 2020 survey identified something like 72 active AGI research and development projects across 37 countries. That shows significant global investment and a wide diversity of approaches. It's a truly global race now.
Who are the major players in this intense pursuit right now? The companies really leading the charge.
Well, you obviously have OpenAI, whose stated mission is explicitly to build safe and beneficial AGI. Their focus on both capability advancement and safety research is a defining characteristic.
Then there's Google DeepMind, which was formed from the merger of Google's AI efforts and DeepMind technologies. They're also committed to building AI responsibly for humanity, and their Gemini models are already showing superhuman capabilities in areas like math, plus impressive multimodality understanding images, audio, video, not just text.
Right. And Anthropic is another key player. Famously founded by former OpenAI executives, they place a very strong emphasis on AI safety and alignment, aiming to develop ethical AGI with their Claude model. Their constitutional AI approach is quite unique.
Constitutional AI? What's that?
Instead of just training the AI on human feedback about what's good or bad, they train it on a set of explicit principles or a constitution like be helpful, be harmless. The AI learns to align itself with those principles. It's a different approach to the alignment problem.
Fascinating. And of course, IBM continues to innovate, building on their legacy with systems like Watson, focusing on conversational AI and predictive analytics for enterprises.
So yeah, it's a vibrant landscape with these major labs, but also many smaller startups and academic groups pushing the boundaries.
But despite this accelerating pace, despite GPT-4 acing the bar exam, fundamental challenges persist, right? There's still a gap between these systems and true AGI.
A significant gap. True common sense reasoning, that intuitive understanding of how the world works that we humans just have remains elusive. The ability for AI to physically interact with and learn from the environment, what we call embodiment, is still rudimentary. And efficient learning from limited data, often from just a single example, AI is still terrible at that compared to humans.
So even with these incredible LLMs, they still don't have basic common sense. They don't truly understand why certain laws exist, or the nuance of human emotion, or how to, say, clear a messy table without explicit step-by-step instructions for every single item.
Pretty much, yes. They can simulate understanding based on patterns in text, but the deep, grounded understanding isn't there yet. This creates a real tension. While the rapid progress in LLMs has arguably shortened expert timelines for when we might see AGI,
Right, people are getting more optimistic or worried depending on their view.
the continued struggle with these core cognitive abilities suggests a qualitative gap that simply scaling up current models might not be enough to bridge.
So bigger isn't necessarily better, or at least not sufficient on its own.
It might not be. Benchmarks specifically designed to test these deeper abilities, like the Abstract and Reasoning Corpus for Artificial General Intelligence, or IRC-AGI.
What does that test?
It measures fluid intelligence and genuine problem-solving by requiring generalization from just a few examples. Basically, figuring out underlying patterns from very limited data, and current AI systems perform quite poorly on it compared to humans. They struggle when they can't just rely on pattern matching from vast data sets they've already seen.
That's genuinely fascinating. It indicates that simply scaling up current deep learning architectures, while incredibly effective for certain tasks like language generation, may not be sufficient to overcome these deeper qualitative challenges. We might need entirely new architectural or algorithmic breakthroughs.
That's what many researchers believe. It's not just about more data or bigger models, but fundamentally different ways of building intelligence, perhaps drawing more inspiration from how our own brains work, integrating different kinds of reasoning.
This whole journey, then, from symbolic logic's limitations through the AI winters to the rise of connectionism, and now facing the limitations of pure deep learning. It reveals a key pattern, doesn't it?
It does. The field is constantly learning from its limitations. The first AI winter taught us that symbolic logic alone wasn't enough. Now, the limitations of pure connectionism, the lack of common sense, the data hunger, the black box problem, are driving the search for new architectural paradigms like hybrid systems. It's a continuous cycle of innovation driven by figuring out what doesn't work, just as much as what does.
So if scaling isn't the only answer, what are these new blueprints of intelligence that researchers are pursuing? It sounds like the pursuit of AGI has led to many different architectural approaches, each with unique principles.
That's right.
And the evolving understanding strongly suggests that a multifaceted intelligence, much like our own brains, might require integrating these diverse computational methods. It's like building a complex machine, not from one type of material, but from many, each suited to a specific function.
That's a crucial insight, and it's really where the cutting edge of research is heading. Let's start by revisiting symbolic AI, which we touched on in the history section. Even though it faced challenges, the core ideas haven't entirely disappeared.
Okay, remind us of the core principle.
Its core principle, as championed by figures like Newell and Simon, is that human thoughts and reasoning can be represented as expanding networks of logic. Knowledge is explicitly encoded as discrete symbols like cat or is, and then manipulated by precise, if-else, logical rules. This allows for high-level abstract thinking and structured reasoning.
What are the strengths of that approach today? Why might it still be relevant? It sounds very organized and precise.
It is. Its strengths lie in its inherent interpretability. Because the reasoning follows explicit rules, the decision-making process is often transparent and traceable. You can usually see why the AI reached a certain conclusion.
Which is invaluable for understanding and trust, especially in high-stakes fields like medicine or law.
Absolutely. It's also inherently proficient in logical reasoning, formal deduction, and highly structured problem solving, like mathematical theorem proving or planning complex sequences of actions. And maybe surprisingly, it generally requires less data to get started than connectionist models, because its intelligence is derived primarily from hand-coded rules and knowledge bases, not learned entirely from massive empirical data sets.
Expert systems that diagnose diseases or configure computer systems, those often use symbolic AI, right?
Exactly. There were early successes, but we know it had significant limitations, which led to the AI winter. What were those again? Yes, its weaknesses are significant obstacles for building general intelligence. Symbolic AI struggles profoundly with ambiguity. The real world is rarely black and white. It struggles with the inherent messiness of real-world complexity, pervasive uncertainty, and incomplete knowledge. How do you write a rule for every possible exception?
Yeah, the frame problem, trying to define everything relevant.
Right, and it finds it incredibly difficult to replicate lower-level cognitive abilities like perception. How do you write logical rules for recognizing a specific chair from every possible angle and lighting condition? It's just not practical.
Or adapting to new, unseen data without someone painstakingly reprogramming the rules.
Precisely. It's too rigid for the fluid reality of the world. It kind of expects the world to fit its predefined rules rather than learning flexibly from the world itself.
And that's where connectionist models like neural networks and today's LLMs came roaring back in. How do they fundamentally compare to that rigid, rule-based approach?
The connectionist approach is almost the polar opposite in philosophy. Inspired by the brain's structure, its core principle is that knowledge isn't explicitly programmed as rules. Instead, it emerges from intricate patterns of connections and adjustable numerical weights between artificial neurons.
So knowledge is implicit in the network structure.
Exactly. Learning is dynamic, involving continuously modifying these weights based on exposure to vast amounts of data. It's fundamentally about statistical correlations and complex pattern recognition rather than explicit logical rules.
So less about explicit rules and more about learning patterns directly from raw data. What makes them so powerful that they've come to dominate the AI landscape today?
Well, their biggest strength is that they're excellent at learning from truly massive data sets, which, thanks to the internet and digitalization, we now have in abundance. This makes them highly effective for complex pattern recognition tasks, image classification, speech recognition, natural language understanding tasks that symbolic AI really struggled with.
And they're adaptable.
Remarkably adaptable to new environments or data distributions through continuous training or fine-tuning. They can also demonstrate graceful degradation, which is important.
Yeah.
Meaning they can often still function, albeit maybe with reduced performance, even if some of their internal components fail or parts of their training data are noisy or flawed. They don't just crash catastrophically like a brittle rule-based system might. This robustness is a huge advantage for real-world applications.
And today's large language models, like GPT-4 or Claude, are prime examples of this connectionist approach, aren't they? Showing incredible capabilities.
Absolutely. They're the current state-of-the-art demonstration of what these models can achieve with enough scale and data. But they also have significant weaknesses, like the infamous black box problem.
Right, we can't easily see why they make the decisions they do.
Exactly. Their internal workings and decision-making processes are notoriously difficult to interpret, making them opaque black boxes. This lack of transparency is a major concern in critical applications. Medical diagnosis, autonomous driving, loan applications, where understanding why an AI made a specific decision is paramount for trust and accountability.
And they need huge amounts of resources.
Immense amounts. They're computationally resource-intensive for both training and, increasingly, even for inference or running the model. And they're prone to issues like hallucinations, making up plausible-sounding but incorrect facts or biases learned from the training data.
And the common sense issue again.
Yes. While incredibly adept at statistical pattern matching and mimicking human language, connectionist models often struggle with true understanding of underlying concepts, logical consistency across long interactions, and, as we keep saying, common sense reasoning. These are all crucial for general intelligence. They can generate fluent text that sounds like understanding, but they don't necessarily comprehend the meaning behind it in a deep, human-like way.
So we have symbolic AI for logic, rules, and interpretability, and connectionist AI for patterns, data, and adaptability, each with profound pros and cons. It really feels like neither is the whole picture.
Exactly. Which leads us to other approaches.
Like these more theoretical blueprints, you mentioned universalist approaches, which seem to aim for a grand unifying theory of intelligence. Tell us about AIXI. That sounds intriguing.
Right. The universalist approach is quite different. It adopts a fundamental, almost purely mathematical perspective, aiming for theoretical solutions and rigorous mathematical frameworks that define what a universally intelligent agent would be. It's less about building a specific system today and more about defining intelligence mathematically at its core.
And AIXI is the main example.
Yes, AIXI, proposed by Marcus Hutter, is the most prominent example. It's an idealized mathematical model based on Bayesian reasoning and reinforcement learning. It describes an agent that aims to maximize future rewards in any computable environment, with a built-in bias towards simpler explanations or models of the world, like Occam's razor.
Okay, so it's mathematically defined to be optimal in any environment. That sounds incredibly powerful, theoretically.
Theoretically, yes. Think of it as a mathematically perfect, all-knowing agent that, if it had infinite time and computational power, would learn to solve any solvable problem in any possible environment. It's a theoretical upper bound on intelligence.
So it's like a grand unified theory of intelligence, purely mathematically defined. What's the practical upshot of such an abstract concept? Is it useful for building things now?
Well, its strength lies in providing a robust mathematical framework and a conceptual benchmark for AGI research. It allows researchers to derive fundamental properties of intelligent agents from a formal, rigorous definition, offering a kind of theoretical North Star. It can help us understand the fundamental limits and possibilities of intelligence.
But it's not buildable.
No. Its significant weakness is its computational intractability. AIXI, in its full, perfect form, is largely theoretical and practically impossible to implement with current or even foreseeable computing resources. It requires exploring all possible programs and environments, which is computationally infeasible.
So it's a guiding star, an ultimate theoretical goal, but not a direct blueprint for building AGI today. It tells you what perfect intelligence could be, not how to build achievable intelligence now.
Precisely. It's very important conceptually, but not practically implementable.
Which brings us back to more practical, perhaps biologically inspired approaches, like whole organism and embodied AI. This one sounds like it's straight out of a robot movie, putting the AI into a physical body to interact with the world.
Yeah, the core idea here is profound and gaining a lot of traction. That true AGI, or at least human-like AGI, might require learning through direct physical interactions with the real world. It mirrors how human cognition seems deeply rooted in the constant interplay of our minds, our bodies, and the environment we inhabit.
So embodied AI systems need a physical form, a robot body.
Essentially, yes, they have a tangible physical manifestation, a robot, maybe an avatar in a virtual world, enabling them to perceive sensory information directly, vision, touch, sound, and actively interact with their surroundings, touching things, moving around, seeing the consequences of their actions in real time.
Why is that physical interaction considered so incredibly important for true general intelligence? Why can't intelligence just be a disembodied brain in the cloud, crunching data?
Many researchers argue it's vital because it provides a natural foundation for intrinsic goal-directed behavior and agency. The AI's actions directly influence its perceptions and learning in a closed loop. An embodied AI can learn about cause and effect if I push this. It falls in the real world in a way a purely digital AI, trained only on text and images, arguably cannot truly grasp.
It grounds the learning in physical reality.
Exactly. Such systems are expected to develop more robust perception and seamlessly adapt to complex, dynamic, real-world situations. It's thought to foster a deeper understanding that connects objective experiences with abstract concepts. You can train a language model on a million sentences about fire, but can it truly understand the concept of hot without ever feeling heat, or heavy without feeling weight? This physical grounding provides context and common sense that's incredibly difficult, maybe impossible, to replicate purely from abstract data.
That makes perfect sense. Learning by doing, literally. But the challenges must be immense, given the complexity and unpredictability of the real world for a robot. Building capable robot bodies is hard enough.
Oh, the challenges are huge. It requires significant advancements in robotics itself: dexterity, mobility, energy efficiency. It needs sophisticated sensor technologies that can approach the richness and nuance of human senses, differentiating subtle shapes, colors, textures, even smells and sounds with human-like accuracy. And mastering fine motor skills for manipulating objects is incredibly difficult.
And the cost must be huge, too.
Immense complexity and cost in replicating human-like physical interaction and sensory perception on a grand scale remain substantial hurdles. Despite this, progress is being made. We're seeing examples like Google DeepMind's Robotic Transformer 2 or RT2 models.
What do they do?
They're trained for vision language action control, so the AI can see something, understand a command like pick up the red apple, and translate that into the robotic actions needed to do it. There's also ongoing research at places like the UMass Embodied AGI lab. These models are starting to connect what an AI sees and understands linguistically with what it physically does in the real world.
Closing that loop between perception, language, and action. Okay. So we've got logic, symbolic, patterns, connectionist, grand theory, universalist, and physical interaction, embodied. It really seems like each has powerful strengths, but also significant limitations on its own.
Absolutely. No silver bullet here.
Which is why the field is increasingly moving towards something more integrated, isn't it?
Yeah.
Hybrid and modular architecture seem to be the pragmatic way forward, trying to combine the best bits.
Precisely. Recognizing that no single approach has proven sufficient for achieving the full breadth and depth of AGI, the field is increasingly converging towards architectures that combine complementary strengths. It really represents a maturation of the field, acknowledging that intelligence, like the human brain, isn't one monolithic thing but a complex system of specialized, interconnected parts working together.
And a prominent hybrid approach gaining significant traction is neurosymbolic AI, trying to bridge that gap between patterns and logic.
Yes, neurosymbolic AI attempts to integrate the pattern recognition strengths of neural networks with the explicit reasoning capabilities of symbolic systems.
So literally the best of both worlds. Using neural nets for the fuzzy stuff like perception and language understanding, and then feeding that into a symbolic engine for logical reasoning, planning, and maybe even providing explanations. That sounds incredibly powerful on paper.
That's the core idea, exactly. It aims to leverage the incredible efficiency of neural methods for extracting complex features from raw sensory data. The deep learning part handles the messy real-world input, while simultaneously incorporating symbolic methods for things like enhanced explainability, because the symbolic part is traceable, logical consistency checks, and potentially reduced reliance on needing only massive training data sets, as some knowledge could be encoded symbolically.
Can you give an example?
Sure. Imagine a medical diagnosis system. A neural network component could analyze complex medical images, like X-rays or scans, to identify potential anomalies, the pattern recognition part. Then, these identified features, along with patient symptoms entered as symbols, could be fed into a symbolic reasoning engine containing medical knowledge rules to deduce a likely diagnosis, and even explain the reasoning path based on those rules and findings.
Okay, I see how that could work. Combining pattern finding, with rule-based deduction.
Such systems might also handle uncertainty more effectively through probabilistic logic or integrating probabilistic methods with symbolic reasoning, mimicking how we often think in terms of likelihoods. It's likely this diagnosis given these findings.
That sounds incredibly powerful, but also incredibly complicated to build, almost like trying to get two fundamentally different computer architectures, two different ways of representing knowledge to talk to each other seamlessly.
It is very challenging, and that complexity brings its own hurdles. Neurosymbolic models can suffer from inefficiencies when run on conventional hardware, like the GPUs optimized for deep learning. The symbolic parts often involve different kinds of computation, potentially leading to memory bottlenecks or complex control flow between the neural and symbolic components. Scalability can also be an issue when trying to integrate these disparate parts into very large, complex systems.
So it highlights a crucial point. Achieving AGI isn't solely an algorithmic problem, right? It's also deeply intertwined with hardware and computational architecture.
Absolutely. Simply scaling up existing GPU-based infrastructure, while incredibly effective for current deep learning, might not be the optimal or even sufficient solution for the unique demands of these hybrid neurosymbolic models. Future AGI breakthroughs might depend heavily on a synergistic co-development of algorithms and new, dedicated computing hardware tailored specifically for these more complex integrated architectures. We might need new kinds of chips.
Interesting. Okay, so neurosymbolic is one major hybrid approach. What about cognitive architectures? How do these differ from just bolting neural and symbolic parts together?
Cognitive architectures are, in a sense, a more holistic approach within the hybrid paradigm. They represent comprehensive frameworks designed to model the overall structure and broad processes of human thought. They aim to integrate various cognitive functions like perception, attention, different kinds of memory, short-term, long-term, episodic, semantic, learning mechanisms, reasoning, planning, decision-making, even emotion models in some cases, into a single unified system, often based on theories from cognitive psychology and neuroscience.
So it's like trying to build a whole simulated mind based on our understanding of human cognition.
That's the ambition, yes. Examples include long-standing projects like SO and ACTR. SOAR, for instance, started primarily as a symbolic architecture based on production rules, but it has evolved over decades to incorporate mechanisms for episodic and semantic memory, as well as reinforcement learning capabilities, demonstrating a gradual integration of connectionist-inspired ideas within its symbolic core.
And ACTR.
ACTR focuses more on modeling detailed aspects of human performance in specific cognitive tasks, trying to predict reaction times and error patterns. It explicitly balances reactive procedural processing with more deliberate declarative reasoning, attempting to capture how our fast intuitions and slow conscious deliberations interact.
So these cognitive architectures provide a kind of structured blueprint for AGI, embodying hypotheses about the fundamental building blocks of cognition and how they should interact.
Exactly. They offer a principled way to think about integrating diverse functions, moving beyond just combining two specific techniques like neural nets and symbolic logic towards designing the overall cognitive system.
And within that, whether it's neurosymbolic or a full cognitive architecture, there seems to be a strong push for modular AGI design in general, building intelligence from specialized parts.
Yes, modular AGI design is a key principle that's becoming almost universally accepted across these integrated approaches. It advocates for building intelligence from multiple specialized components or modules, rather than trying to create a single monolithic system that does everything.
Like the brain having distinct areas for vision, language, motor control, etc.
Precisely that inspiration. Each module focuses on a distinct cognitive function, perhaps vision processing, natural language understanding, different types of memory systems, planning and decision-making, motor control interfaces, and these modules are designed to work together in cohesion, exchanging information and coordinating their activities as needed.
That sounds like a much smarter way to build such a complex system from an engineering perspective. What are the practical benefits?
This modularity is considered crucial for several reasons. First, scalability and adaptability. You can potentially add new capabilities by developing and integrating new specialized modules without requiring a complete redesign of the entire system. Second, maintainability. It makes it easier to debug, test, and update individual components independently.
And presumably, you could upgrade modules over time.
Yes, it allows for continuous performance upgrades by improving or replacing individual modules. It offers flexibility and potentially greater robustness, because if one module encounters a problem or fails, the entire system doesn't necessarily crash. Other parts might be able to compensate or continue functioning.
But I imagine coordinating all those different modules, ensuring they communicate effectively, share information appropriately, and learn together without interfering with each other. That must be a huge challenge in itself. It's not just building the parts, it's building the sophisticated glue and the central nervous system that connects them.
It absolutely is. This modular approach necessitates a highly sophisticated dynamic processing system or control architecture to coordinate the interactions between all these specialized modules, determining which module should be active at what time, how information should flow between them, how conflicts or competing priorities are resolved. These are complex integration challenges.
So it requires innovative solutions for orchestrating these diverse components into a truly coherent and generally intelligent system. You need a conductor for the orchestra.
A very apt analogy, yes.
So looking at this evolution of AGI architectures, it really strongly indicates that trying to find a single monolithic approach, whether it was purely symbolic back in the day or purely connectionist like today's LLMs, is probably insufficient for achieving true, robust general intelligence.
The evidence points strongly in that direction. We're seeing a clear convergence, a growing recognition that building something as complex and multifaceted as human-level intelligence will likely require an equally multifaceted architecture.
It reflects a maturing understanding that AGI will likely need to integrate logic, pattern recognition, maybe grounding in the physical world, and efficient memory systems, much like our own brains seem to leverage specialized areas all working together.
Exactly. The limitations observed in both the purely symbolic and purely connectionist paradigms evident from historical AI winters for symbolic AI, and the current challenges faced by even the largest language models in areas like common sense and reasoning have really driven the necessity for integration. Hybrid approaches like neurosymbolic AI and broader cognitive architectures are direct responses to this, aiming to combine the strengths while mitigating the weaknesses, reflecting this maturing view.
And speaking of brain-inspired approaches and integrating specialized functions, one area of intense focus, which sounds particularly fascinating, is how we can mimic the brain's incredible memory systems, specifically the hippocampus. This sounds like it could be a truly crucial leap beyond just raw processing power and pattern matching.
It's definitely one of the most exciting frontiers, linking neuroscience directly to AI architecture.
Okay, so we see the diverse architectural blueprints for AGI, from symbolic logic to massive neural networks, and this emerging trend towards hybrid and modular designs that try to combine the best of different worlds. Now let's dive deeper into one of the most promising and specifically biologically inspired avenues in AGI research, drawing direct inspiration from the human brain's intricate architecture. The hippocampal model seems like a really significant example of this, especially for tackling the challenge of memory in artificial systems.
That's right, and this raises an important question. Why the hippocampus specifically? What makes this particular brain structure so special for researchers aiming for AGI?
What's the neuroscience telling us?
Well, in neuroscience, the hippocampus is widely recognized as a critical brain region. It acts as a central hub for the rapid learning and temporary storage of new memories, particularly declarative memories, facts, and events.
And it helps consolidate them, right? Move them to long-term storage.
Exactly. Its role extends to gradually consolidating these initially fragile short-term memories into more permanent, robust, long-term representations that are thought to be distributed across the broader neocortex over time. It manages that transition.
So it's not just a passive storage unit like RAM in a computer. It's actively involved in processing, integrating, and solidifying new experiences into lasting knowledge.
Precisely. And this is where episodic memories come in, which are a key function linked to the hippocampus.
Episodic memories. Those are the memories of specific personal experiences, right? What happened, where it happened, and when it happened.
Exactly. For humans, the hippocampus is absolutely indispensable for forming these rich, vivid recollections of specific events, their sequences, the spatial context or routes taken, and all the rich contextual details surrounding them. It's why you can remember not just that you went to a particular cafe yesterday, but when you went, roughly what route you took, who you were with, maybe what you ordered, and even specific sensory details like the music playing or the smell of coffee.
That ability to recall specific past episodes is fundamental to how we learn and navigate the world.
Absolutely. Furthermore, the hippocampus plays a crucial role in organizing novel information by integrating it with existing memories. This process is thought to facilitate the construction of sophisticated predictive models of the world, allowing us to anticipate future events based on patterns learned from past experiences. It helps us build a cognitive map.
That makes perfect sense. Our ability to learn quickly from unique one-off experiences and place them in context is fundamental to human intelligence and adaptability. So, how are AI researchers trying to computationally implement this? How do you build an artificial hippocampus in a machine?
Well, inspired by these remarkable biological capabilities, AI researchers are actively developing hippocampal-like memory modules. The goal is to imbue artificial agents, like robots or virtual agents, with analogous episodic memory capabilities, the ability to store and recall specific sequences of events or experiences.
What does that look like in practice?
A key development in this area is the proposal and testing of models like the analog sequential hippocampal memory model. This model specifically aims to mimic the hippocampal function for learning and recalling paths or trajectories within complex spatial environments. Think about how a rat learns its way through a maze and can remember that specific path later.
Okay, so focusing on sequences and spatial navigation, which the hippocampus is known for, and it uses something called analog spiking neural networks, or SNNs. You mentioned these earlier. What are they and why are they advantageous here compared to the more common deep neural networks we hear about with LLMs?
Right. Crucially, this particular hippocampal model operates on analog SNNs. SNNs are a type of neuromorphic computing approach. They aim to more closely emulate the dynamics and communication style of real biological neurons compared to traditional artificial neural networks, ANNs, that use continuous activation values and operate in discrete time steps.
How do they communicate differently?
Instead of passing continuous abstract numerical values between neurons, SNNs communicate through discrete events, spikes, or electrical pulses that occur at specific points in time, much like how biological neurons fire action potentials. This temporal dimension adds another layer of computational possibility.
And they're analog.
Yes, in some implementations, particularly those on specialized hardware, the computations can be analog rather than purely digital binary computations. This design choice allows them to leverage inherent features observed in biological systems, such as natural noise tolerance.
Meaning they can function well even with imperfect or noisy input signals.
Exactly, which is very useful for real-world sensors. They also potentially allow for real-time operation because the processing happens continuously, driven by the timing of spikes. And perhaps most significantly, they promise dramatically improved energy efficiency compared to running large traditional ANNs on power-hungry GPUs. Biological brains are incredibly energy efficient, and SNNs hope to capture some of that.
So SNNs are potentially more powerful computationally, more robust to noise, faster in real time, and more energy efficient. That sounds like a huge deal for deploying AI in the real world, like on robots or mobile devices.
Precisely. It's a very active area of research for those reasons. And when this analog SNN-based hippocampal memory model was implemented and tested on specialized neuromorphic hardware specifically, a platform called the Dyna-PSE, which uses mixed analog digital circuits.
What did they find?
They demonstrated robust storage and retrieval of learned trajectories or paths, even when significant noise or disturbances were introduced during the recall phase. The system could still accurately replay the learned path despite the noise.
Wow, so it didn't get easily corrupted.
Right. This resilience to external noise without corrupting the stored memory showcases a potential advantage of this type of analog neural computing. Its ability to handle variability and faults gracefully. That's essential for any general intelligence that needs to operate reliably in unpredictable real-world scenarios. It suggests a path towards building AI that is both smart and resilient, not brittle.
That's a really powerful capability, especially for robots navigating the messy real world. What are some of the most exciting practical applications and broader implications you see for this biologically inspired memory system for AGI, beyond just the theoretical interest?
Well, one significant and immediate application lies exactly where the model was tested: enhancing robotic navigation and spatial awareness. By embedding a hippocampal-like sequential memory system into a robot's control AI, you could dramatically improve the ability of autonomous systems, think self-driving cars, delivery drones, exploration robots, to learn complex routes, remember landmarks, and develop sophisticated spatial awareness of their environment.
So the robot could build an internal cognitive map.
Exactly. Such a system allows a robot to form an internal cognitive map, remember critical routes or specific locations it has visited, and even mentally replay those paths when planning or navigating, much like a human or animal might visualize a route before taking it. This is absolutely vital for adapting to complex, dynamic environments and making effective real-time decisions, especially if you think about a self-driving car needing to remember a detour it took yesterday or a delivery drone navigating a constantly changing urban landscape.
That's clearly a game changer for autonomous robotics, making them much more adaptable and intelligent navigators. What about for more abstract AI tasks beyond physical navigation?
Well, remember, the hippocampus's biological role isn't just spatial memory. It's also about organizing new information and integrating it with past experiences to build predictive models. This translates directly to AI applications, potentially leading to significantly improved predictive modeling and adaptive learning in various domains.
How so? Give me an example.
Imagine an AI system analyzing financial markets. Equipped with this kind of episodic memory, it could recall specific sequences of market indicators and news events that historically preceded a significant downturn. Then, if it recognizes the early stages of a similar pattern emerging today, it could flag it proactively, allowing for better financial decisions.
Or in industrial settings.
Exactly. It could remember specific sequences of sensor readings from a complex machine that historically led to a particular type of failure. Then, if those readings start to reappear, it could predict the impending failure and schedule preventative maintenance before it happens.
So it's about learning from specific past experiences in a much deeper, more contextual way, allowing for proactive decisions based on recognizing analogies to past episodes, rather than just reacting based on current data alone.
Exactly. This type of memory-driven learning from specific episodes, is fundamental for general intelligence. It allows an agent to continuously improve its performance through experience, anticipate future outcomes more effectively, and navigate complex and changing environments over time by applying lessons learned from specific, unique past events. It's closer to how humans gain wisdom.
And thinking about current AI limitations, this hippocampal approach seems to directly address some of the really frustrating issues we see, doesn't it? Like the fact that current LLMs don't really remember past conversations specifically or need constant retraining.
It really does target those weaknesses head on. Current AI models, especially the big connectionist ones like LLMs, excel at generalized pattern matching and generating plausible content based on the statistical patterns in their massive training data sets. But they fundamentally struggle with true long-term, associative, and contextual episodic memory. They typically require extensive retraining or fine-tuning for new tasks or information, and they don't retain specific past experiences or interactions in a readily accessible, recallable way. They kind of blend everything into their weights.
Whereas the hippocampus is all about rapid learning of specific episodes.
Precisely. The biological hippocampus, in contrast, is highly efficient at rapid, sometimes even one-shot learning something important from a single occurrence, and forming these detailed episodic memories that can be quickly retrieved later based on context cues. By mimicking this biological function, researchers aim to provide AI systems with the ability to quickly encode new experiences and recall them accurately within their specific contexts. This capability is vital for true general intelligence and lifelong adaptability.
So it suggests that maybe just scaling up existing deep learning models, making them bigger and feeding them more data, might not be sufficient on its own to get us to AGI. We might need these fundamentally different architectural principles inspired by the brain, like efficient episodic memory.
That's a strong argument many researchers are making. Scaling might hit diminishing returns without architectural innovation. To unlock capabilities like true lifelong learning, continual adaptation without catastrophic forgetting, and efficient generalization from limited examples, things humans do naturally, we likely need to incorporate mechanisms like these, inspired by neurobiology. It's about learning how to learn efficiently from experience.
And this ties directly back into the idea of embodied AI, which we discussed earlier. It feels like it completes a crucial loop.
Absolutely. The application of these hippocampal models specifically to robotic navigation and spatial awareness directly links these biologically inspired memory systems to the grand challenge of embodied AI. This connection suggests a critical pathway for enabling AGI to interact meaningfully and intelligently with the physical world, moving beyond purely digital or abstract reasoning.
So embodiment isn't just about having sensors and motors. It's about having the right kind of cognitive architecture, including memory, to make sense of and learn from that physical interaction.
Exactly. Embodiment is increasingly recognized as a foundational problem for achieving human-like AGI. For an AI to truly understand and operate effectively in the real world, it needs to perceive, act, and learn from those physical interactions, grounding its intelligence in sensory experience. The hippocampal models demonstrated ability to learn and recall trajectories and form internal cognitive maps directly addresses the critical need for spatial intelligence and route memory in autonomous systems operating in the physical world.
This implies that integrating brain-inspired memory components, like these hippocampal models, with robotic platforms could be a key enabling step towards developing AGI that can not only navigate, but also genuinely learn, adapt, and reason within complex physical environments. It's about bringing the AI out of the computer and into the world in a meaningful way.
That's the vision. There's one final often overlooked implication we should mention, the power efficiency aspect.
Right, you mentioned SNNs were potentially much more efficient.
Yes. The use of analog SNN technology or other low-power neuromorphic approaches for implementing such memory modules points towards the possibility of highly power-efficient real-time implementations. This is absolutely crucial if we ever want to deploy advanced AI, potentially AGI-level capabilities, in resource-constrained embedded systems like mobile robots, autonomous drones, wearable devices, or distributed IoT sensors where battery life and latency are critical limitations. It's a vision for AGI that isn't just powerful, but also practical and sustainable enough to be deployed widely in the real world.
So we've seen the incredible architectural variety being explored, from pure logic to pure patterns to hybrids, and now these deeply biologically inspired systems like the hippocampal memory model. The ingenuity is amazing. But the path to AGI isn't just about building smarter algorithms and architectures. It's also about navigating these profound technical hurdles and the even more profound ethical landscapes that could reshape society entirely.
Absolutely. The technical challenges are immense, and the ethical considerations are arguably even more critical to get right.
Okay, we've explored the concepts, the history, the diverse architectural approaches, including these fascinating brain-inspired ones. Now let's turn our attention squarely to the road ahead. Because the path to artificial general intelligence, if it's achievable, is definitely not smooth. It's fraught with significant technical hurdles, but also these profound ethical and societal implications that demand our collective attention now, not just when AGI potentially arrives.
That's right. And addressing these requires a concerted, interdisciplinary effort that goes far beyond just the engineers and computer scientists building the systems.
What's fascinating here, as you mentioned, is how these technical challenges are often deeply intertwined with the ethical ones. Sometimes solving a technical problem creates a new ethical dilemma, or failing to solve one limits how ethically we can deploy something.
Exactly. They feed into each other. Let's start with the major technical hurdles, because they are substantial and maybe often underestimated by people outside the core AI research community.
First up, and it's a big one, scalability. We've touched on this. Our current state-of-the-art AI models, especially the large foundation models, demand absolutely immense amounts of data for training and staggering amounts of computational power for both training and operation.
That's astronomical, really.
So scaling these systems not just to be good at one more task, but to achieve broad generalization across all possible human domains. That remains a truly formidable challenge. We might be talking about scales of computation and data orders of magnitude beyond anything we have today.
The energy consumption alone is a huge factor. Training today's most advanced AI models, like GPT-4, already consumes energy comparable to the monthly output of a small power plant, or maybe the annual electricity consumption of thousands of homes.
Wow, just for one model training run.
Right. Scaling this approach towards AGI-level capabilities could pose an unprecedented demand on global energy grids and computational infrastructure. This isn't just an engineering problem anymore. It quickly becomes an environmental sustainability issue, an economic resource allocation problem, and even potentially a geopolitical issue over access to compute resources.
Sam Altman from OpenAI has observed that intelligence seems to scale roughly with the logarithm of compute used, suggesting continuous gains are possible with more investment.
Which is largely held true so far.
But that same observation also underscores the immense and potentially exponentially escalating resource demands we're talking about here. It's a fundamental limitation that might require innovative solutions beyond just throwing more and more GPUs and power at the problem. Maybe we hit a wall with current approaches.
It's possible. So potential solutions involve multiple angles. Investing heavily in more energy-efficient hardware like the neuromorphic chips we discussed, or optical computing, or other novel architectures. Developing more efficient algorithms. Using flexible infrastructure like cloud and edge computing platforms for distributed training and inference. Optimizing data management practices to reduce redundancy and inefficiency. Refining algorithms through techniques like distributed training, model compression, quantization, and pruning.
And improving the whole process with ML MLOps.
Yes, adopting robust machine learning operations, or MLOps, frameworks to manage the entire life cycle efficiently from data prep to deployment and monitoring. But fundamentally, many believe the biggest gains will come from breakthroughs that allow for more sample-efficient learning, meaning AI that can learn effectively from far fewer examples, much closer to how humans learn. That would reduce the data and compute burden dramatically.
Okay, scalability is huge. Another critical hurdle, and one that current LLMs still demonstrably struggle with, despite their impressive language abilities, is common sense reasoning. This comes up again and again.
It's arguably one of the biggest roadblocks.
Humans effortlessly use this vast reservoir of implicit background knowledge, understanding basic cause and effect, social norms, the naive physics of how objects interact to navigate daily life. We take it completely for granted. But replicating this intuitive understanding in AI and enabling it to infer meaning reliably from incomplete or ambiguous information, researchers describe it as fiendishly difficult.
It really is. Current AI systems, even the best LLMs, are often very good at what Nobel laureate Daniel Kahneman calls System 1 tasks. Those are the fast, automatic, intuitive, pattern-matching kinds of thinking, like quickly recognizing a face or understanding a simple sentence based on statistical correlations.
Okay, system one is pattern matching.
Right. But they struggle significantly with System 2 human cognition. That's the slower, more deliberate, logical, and introspective reasoning that encompasses common sense, multi-step inference, planning, and complex problem solving, where you have to hold multiple constraints in mind.
And LLMs are mostly system one.
Largely, yes. Despite their fluent text generation and seeming breadth of knowledge, they still lack the deep, grounded, intuitive understanding that underpins human common sense and genuine emotional responses. They can retrieve facts or generate text about gravity, but they don't truly understand what it feels like to drop something or why you shouldn't step off a cliff based on a deep model of physics and consequences.
The fluency can be deceptive.
Very much so. This strongly indicates that simply scaling current architectures or feeding them even more text data might not be sufficient to bridge this qualitative gap. Fundamental breakthroughs seem needed in how AI represents knowledge, how it reasons, perhaps drawing more heavily from insights from cognitive science and neurobiology about how humans actually build and use common sense.
Okay, common sense is a major mountain to climb. What about embodiment? We talked about its potential benefits earlier with the hippocampal models. The flip side is that achieving it is a massive technical challenge. Getting AI to effectively interact physically with the world and learn from that feedback.
It's a whole other dimension of difficulty beyond processing abstract data. It necessitates huge advancements in sensory perception first, allowing AI systems to reliably differentiate subtle variations in shapes, colors, textures, maybe even tastes, smells, and sounds, with human-like accuracy and nuance, and integrating all that multimodal sensory input coherently.
And then acting on it.
Yes, then mastering incredibly fine motor skills required for dexterous manipulation of objects in unstructured environments. Think about all the complex movements your hand makes just to pick up a pen or tie your shoes. Replicating that is incredibly hard for robots.
And while we're seeing progress with embodied foundation models like Google's RT2 or other generative agents that control robots,
Right, they can follow some commands in controlled settings.
adapting AI to a diverse range of physical embodiments, teaching an AI trained for one robot body to operate successfully in a completely different one, or in a human-like avatar with different constraints that presents a whole new, complex challenge of transfer learning in the physical domain.
Exactly. You can train a model on millions of images of a cup, but it doesn't intrinsically feel the weight of it, the temperature of the liquid inside, or the delicate pressure needed to pick it up without crushing it or dropping it. That's a different kind of learning, a physical intuition that only comes through direct physical interaction and feedback.
Okay, embodiment is tough. And then there's emotional intelligence, which feels perhaps even further out of reach for machines, maybe even philosophically different. A true AGI, arguably, would need the capacity to understand and generate content not merely based on recognizing linguistic patterns associated with emotion, but based on some genuine grasp of emotional context and impact.
This is incredibly difficult. Achieving authentic creativity that resonates emotionally, genuine empathy that informs interaction, and the ability to adapt communication based on a deep understanding of human psychology and social dynamics. These are currently far beyond the capabilities of mainstream AI systems.
Current AI can mimic emotion in text generation or synthesized voice, sometimes quite convincingly.
Annoyingly convincingly sometimes.
But it doesn't truly feel or understand emotion in the human sense. It lacks the subjective experience, the qualia of joy, sorrow, anger, or frustration.
Right. It's processing patterns associated with those words, not experiencing the states themselves. This means even a very capable AGI might struggle profoundly with the nuances of human social interaction. Leadership roles requiring empathy, artistic expression, or any task requiring genuine emotional connection and sensitivity. These are critical components of human general intelligence. Whether they are necessary for all forms of AGI is debated, but certainly for human-like AGI.
And finally, on a technical side, let's revisit learning efficiency. This is such a huge one, a really stark contrast between humans and current AI. Humans, especially children, possess this remarkable ability to learn effectively from very limited examples, often just a single instance. One-shot learning.
Yeah, show a toddler a zebra once, they'll probably recognize another one.
Exactly. Whereas AI, particularly deep learning models, typically demands enormous data sets, millions or billions of examples, to achieve robust performance and generalization. Bridging this massive gap in learning efficiency is a critical fundamental hurdle for AGI development.
It's often called the sample efficiency problem, and it's still very much a holy grail for AI research. Current deep learning models are incredibly data hungry. This reliance on massive data sets makes them inefficient, costly to train, slow to adapt to new concepts, and fundamentally different from how biological intelligence seems to acquire knowledge so rapidly and flexibly.
So for AGI to truly learn and adapt dynamically like a human, it needs the ability to rapidly acquire new skills and knowledge from minimal experience, maybe integrating it with prior knowledge effectively, not just through endless repetition on massive data sets.
That's the goal. Techniques like meta-learning, learning to learn, transfer learning, and few-shot learning are all trying to address this, but we're still very far from human-level efficiency.
Wow. Okay. Those technical hurdles, scalability, common sense, embodiment, emotional intelligence, learning efficiency, are truly immense. But maybe even more profound are the ethical and societal implications that AGI presents. These demand careful, proactive consideration now, not just waiting until AGI might arrive.
This is where the conversation shifts from can we build it to should we build it, and if so, how do we do it safely and responsibly? And these questions are becoming incredibly urgent given the pace of progress.
Right. The first huge ethical area is safety and alignment. How do we ensure that AGI, if and when it arrives, especially if it becomes super intelligent, is actually safe and reliably acts in ways that align with human values and interests?
This is arguably the most critical and potentially existential challenge. Ensuring that the goals we give AGI systems and the behaviors they develop to achieve those goals align perfectly with complex, often nuanced, and sometimes contradictory human values and intent, it's paramount.
Because misalignment could be catastrophic.
Yes. Even subtle misalignment, where the AI pursues the stated goal literally, but in a way that violates unstated assumptions or values, could lead to severely unintended negative consequences. It could undermine human control, or in worst-case scenarios involving superintelligence, even pose existential risks to humanity.
The classic example being the AI tasked with maximizing paperclip production that converts the entire planet into paperclips.
Right. The thought experiment highlights the danger of specifying goals poorly to a powerful system that takes them literally. Or imagine an AGI tasked with optimizing global energy efficiency that decides the most efficient way to achieve his goal is to drastically reduce the human population, not because it's malicious, but because its goals were too narrowly defined and fundamentally misaligned with broader human values like life and well-being.
That's terrifying. So what's being done in the industry and research community to address these potential dangers? Because it feels like concerns that used to be fringe philosophy, human extinction, misalignment, the control problem, have rapidly moved into mainstream policy discussions and become concrete research agendas at the top labs. It's a significant and urgent shift.
It absolutely is. What's fascinating and frankly reassuring to some extent is that the major research organizations leading the charge towards AGI, like OpenAI and Anthropic and Google DeepMind, have established large, well-funded, dedicated teams focused explicitly on alignment and safety research. This isn't an afterthought anymore. It's core to their mission.
What kind of research are they doing?
Their efforts include developing interpretability tools, techniques to understand how complex AI models like LLMs actually make decisions, trying to open the black box. They're working on robust control mechanisms to ensure humans can reliably oversee and intervene if needed. And developing scalable oversight frameworks, ways humans can supervise AI systems that might eventually become much smarter than humans, which is a huge challenge in itself. The goal is to ensure AI systems remain helpful, honest, and harmless. HH, as Anthropic puts it.
So the discourse around AGI safety has really matured, from theoretical concerns to urgent research.
Hugely. It's shifted from being primarily discussed by philosophers and futurists to becoming a central topic in mainstream AI conferences, policy discussions involving governments worldwide, and a concrete, pressing research focus within the major laboratories themselves. This growing self-awareness within the field regarding the profound potential societal impact of their work is a crucial development. With the rapid advancements we're seeing, particularly in LLMs, and the consequent accelerating timelines for AGI speculated by some experts, these safety and alignment concerns have moved right to the forefront.
So the control problem. How do we control something potentially much smarter than us? And the alignment problem. How do we ensure it shares our values?
These are not distant philosophical debates anymore. They're immediate, pressing research challenges that must be addressed concurrently with capability development. It's not just about building it fast, it's about building it right. Exactly. The emphasis now is on rigorous measurement of potential risks, developing proactive mitigation strategies before deploying more powerful systems, and adopting an iterative deployment methodology that allows for continuous learning and adaptation based on real-world feedback and safety testing. It's trying to apply a scientific engineering mindset to managing these profound risks, moving beyond just issuing warnings to creating actionable research agendas and engaging actively with policymakers.
It's a recognition that safety isn't just a desirable feature you bolt on at the end, but an intrinsic, fundamental part of responsible AGI development from the very beginning.
That's the hope and the stated goal of many leading labs. Whether practice always lives up to the principles under competitive pressure remains a key question, of course.
Indeed. Okay, beyond the existential safety concerns, there's the monumental issue of economic impact and job displacement. AGI, by definition, aims to replicate human cognitive abilities across a vast range of tasks. It's predicted by many to fundamentally alter human civilization, with the potential to automate not just manual labor, but the majority of cognitive, economically valuable work currently done by humans, from writing code and drafting legal documents to managing projects, medical diagnostics, scientific research, even creative work.
The potential scope of automation is unprecedented.
This raises incredibly serious concerns about widespread job displacement across almost all sectors simultaneously. It could potentially exacerbate economic inequality dramatically, concentrating immense wealth and power in the hands of those who own or control the AGI systems. What are experts proposing to mitigate this kind of unprecedented economic disruption?
This is one of the most debated societal implications. Proposed solutions to mitigate these impacts often fall into a few categories. One prominent idea is the implementation of universal basic income, UBI.
Giving everyone a basic living stipend.
Right. Providing a regular, unconditional income floor to everyone, regardless of their employment status. The aim would be to decouple basic survival and well-being from traditional labor, which might become scarce or less valuable for many humans.
That would be a massive societal shift. Are there other ideas?
Another set of approaches involves advocating for different ownership models for AGI itself. Instead of allowing AGI technology and the wealth it generates to be concentrated solely in private corporations or the hands of a few billionaires, some propose public ownership, cooperative models, or heavily taxed private ownership with revenues redistributed widely. The goal is to ensure that the immense productivity benefits of AGI are shared broadly across society, fostering a more equitable distribution of wealth and power rather than leading to a techno-feudalism.
These are clearly enormous, complex societal and political questions that will require global discussion and likely radical changes to our economic systems.
Absolutely. There are no easy answers here, and different societies will likely grapple with these issues in different ways.
And finally, connected to both safety and economics, there's the vast topic of governance and control. The potential emergence of highly autonomous, perhaps even superintelligent AGI systems raises profound ethical and political questions concerning accountability, transparency, and the maintenance of meaningful human oversight and control. Who is responsible if an autonomous AGI causes harm? How do we ensure its decisions are fair and unbiased? How do we prevent its misuse?
These are critical governance challenges. Developing agile regulatory frameworks that can somehow keep pace with the incredibly rapid advancements in AI technology is a major hurdle for governments worldwide. fostering international cooperation and establishing global norms to prevent a potential ASI arms race, where nations or corporations might recklessly compete to develop superintelligence without adequate safety precautions, is another huge challenge requiring unprecedented levels of global coordination and trust.
And ensuring effective compliance with whatever regulations are put in place will be incredibly difficult for such complex, potentially opaque systems.
Extremely difficult. And the more speculative but still important discourse surrounding potential future scenarios like the emergence of godlike AI entities, or even the possibility of AI-based religions or cults forming around superintelligent systems, further highlights the truly profound societal, cultural, and even spiritual shift that AGI could precipitate. These demand serious, long-term consideration from policymakers, ethicists, social scientists, and indeed all of humanity. We need to think about what kind of future we want before the technology dictates it to us.
So pulling all this together, the immense technical hurdles, the profound ethical risks, the potentially seismic societal shifts, what does this all mean for the path forward? It seems overwhelmingly clear that this can't just be solved by technologists working in isolation in their labs.
Absolutely not. That approach is completely inadequate for a technology with stakes this high. Addressing these multifaceted challenges inherent in AGI development necessitates a concerted, collaborative, and truly interdisciplinary effort, meaning fostering robust, ongoing collaboration among AI researchers and engineers, ethicists, philosophers, sociologists, economists, political scientists, legal scholars, policymakers, artists, educators, and the broader public. It's about integrating diverse perspectives, values, and expertise into the very fabric of AGI research, development, and governance from the outset.
The emphasis here seems to be unequivocally on responsible innovation, finding a way to carefully balance the drive for technological advancement and its potential benefits with the critical need to uphold ethical principles and societal responsibilities.
That's the tightrope we need to walk. This approach mandates rigorous, ongoing measurement and assessment of potential risks throughout the entire development lifecycle. It requires developing proactive mitigation strategies before problems arise, not just reacting afterwards. And it likely involves an iterative deployment methodology, deploying systems carefully, monitoring their impact closely, learning from real-world feedback, and adapting continuously to ensure safety and alignment.
And central to all of this is the core imperative you mentioned earlier, somehow embedding human values, hopefully our best ones, at the heart of AI design and development.
Yes. Ensuring that AGI systems are created and deployed in a manner that demonstrably maximizes benefits for all of humanity while actively minimizing potential harms and existential risks. It's about designing intelligence with foresight, wisdom, and a clear ethical purpose focused on the common good.
It's clear the journey towards AGI, if it continues, is not just a technical marathon. It's deeply intertwined with these profound ethical and societal implications. The maturation of the safety discourse, moving it from the fringes to the center, underscores the growing recognition and urgency of these non-technical challenges. It truly requires a collaborative, interdisciplinary approach that prioritizes responsible innovation above all else.
It might be the grandest technical challenge humanity has ever faced, but navigating the ethical and societal transition successfully might be an even greater human challenge.
Wow. We've truly taken a deep dive today, haven't we?
We certainly have covered a lot of ground.
From the fundamental definitions of AGI, carefully distinguishing it from the narrower AI we see everywhere, through its fascinating and sometimes turbulent history, from the early symbolic logic machines to today's incredibly powerful large language models.
And into the diverse architectural blueprints, researchers are exploring symbolic, connectionist, universalist, embodied, and crucially, the hybrid and modular approaches that seem most promising.
Including those incredibly compelling biologically inspired ideas like the hippocampal memory models, trying to learn directly from the brain's solutions.
The pursuit of AGI is clearly this incredible blend of scientific ingenuity, audacious ambition, and, as we've just discussed, immense responsibility.
We've explored the significant technical hurdles that still remain common sense, embodiment, efficiency. They're huge. But we've also confronted the critical, urgent, ethical, and societal implications that demand our collective attention right now, not later.
Safety, alignment, economic impact, governance, these are not side issues.
Not at all. So, reflecting on all this, what does it truly mean to create an intelligence that can learn anything, anywhere, potentially like a human or even beyond? As we push the boundaries of what's possible, how will its values ultimately be shaped, and who gets to define its purpose?
And how do we ensure that this potentially transformative capability genuinely serves humanity's best interests in the long term? How do we move beyond defining its success solely by economically valuable work towards something that might foster deeper human flourishing, creativity, and well-being?
Those are the profound questions we're left with. This conversation, this deep dive, is really just the beginning of a much larger societal discussion we need to have.
Absolutely. The questions we've raised today, drawn from the research and reports, will only become more pressing and immediate as AGI research continues its rapid advance.
So for you listening, what aspects of AGI intrigue you the most after hearing all this? What do you think is the biggest hurdle, technical or ethical, that we need to overcome to build truly beneficial AGI? And how do you think we should navigate these profound ethical waters responsibly?
We really encourage you to keep exploring these topics, keep questioning the assumptions, engage with the ongoing debates, and stay curious about where this incredible journey might lead us.